All right, let's take a review of isotopes and how we calculate atomic mass. All right, so again, remember isotopes are going to differ only in our neutrons. If I change the protons, I change the element, but if I change the number of neutrons, I just have a different isotope. So atoms of an element are identical in atomic number, but not in mass number. Okay, and so we've got our carbon isotopes, carbon 12, carbon 13, and carbon 14. Carbon 14 is our radioactive one. It's the one used in radiocarbon dating. And so we looked at the symbols of those in the previous video. So you can fill those symbols in. When we look at atomic mass, we are looking at a weighted averaging. Now, we have to have a reference point. So our reference point for atomic mass is carbon 12. Carbon 12 is very stable. It's incredibly abundant. It's everywhere. So it's a good reference point. All right, and so we've got our atomic mass units. So 1 AMU is equal to 1/12 the mass of a carbon 12 atom, because if I have carbon 12, then I've got my mass number of 12, so it's 1/12 of that. So 1 AMU is this 1.66 times 10 to the negative 24th grams. All right, now we figure out these masses through mass spec. So we send a sample through, it gets vaporized, it goes through a process where it is then ionized. It goes through some electrical plates, and then it's got a magnetic field in it that then separates things based on the mass to charge ratio. And so lighter things hit the detector first, heavier things hit the detector later, and you get these spikes on your readout that correspond to the percentage of particles at a particular mass that hit the detector. And so here's a simplified look of chlorine. And so we get a higher percentage of the particles for chlorine hit at the mass of 35, lower percentage at 37, which makes sense because our weighted average for chlorine is at 35.45. If we had a perfect 50-50 split, the mass of chlorine would be 36, but we are closer to 35 than to 37, which speaks to having a greater percentage, a greater proportion, be the chlorine 35. Okay, we can do this with all of our elements, and we get all of these different spikes that let us know. Now, we can use mass spec not just for isotopic masses. We use mass spec for all sorts of things because it breaks things apart, and we get this charge to mass ratio. We can get fragments of molecules that help us when we're doing like an analysis of a novel compound to see if we actually have our formula and all that other stuff correct. All right. Okay, so we know that we have to look again at that weighted averaging. So we look at our mass, we multiply the percent by the percent abundance in decimal form. And so here I have the data for silicon. So calculate the atomic mass of silicon. And then we'll pause, calculate that, and then unpause and see if you're correct. Remember, I am looking when you turn your notes in to see that you've actually solved the example problems. Handwrite them, write them out, because I'm not just looking to see that you solved the example problems, I'm also looking to see that you understand and have retained proper dimensional analysis techniques. Okay. This is easy though. So, you know, we're just going to be able to take our masses that way. Okay, so now let's look at this one right here, silver. Okay, so for silver, we've got a mass and percent abundance. I know my face cuts off this down here, but you have the slides that you can download. So download the slides, and again, practice it, and then check to see if you solved it correctly. Okay, and so we have silver 107 and silver 109, so. And again, remember that percent abundance has to be in decimal form. So 51.84% becomes 0.5184. And 48.16% becomes 0.4816. Okay, so silver we should get 107.868. And I can check on a periodic table and verify that I'm on the right track with that. Okay. I can also, if I know the average atomic mass, I can figure out a missing mass. So I can check on the periodic table and I can see for boron that I've got a mass of 10.812. And so I can set up an equation and I can figure out what is that mass of boron 11. Okay. All right, and so that X is going to be the missing boron 11, and then I can use algebra and I can solve for X. And so I'll get 1.98255 plus 0.802x is equal to 10.812. 0.802x is equal to 8.82945. X is equal to 11.0093. So my boron 11.0093 AMU. Okay. Now we actually know these atomic masses to like really, really good precision. We know these out to like super crazy amounts of decimal places. All right, now here's a little bit more challenging one. So I've got chlorine, and I've got an atomic mass of 35.453. Now we've got two isotopes, chlorine 35 and chlorine 37. Now I want to know what the percent distribution between these two is. Now we've seen with chlorine, we know that chlorine's going to have a higher percentage of chlorine 35 because of that average mass. But let's say we didn't run the mass spec, or we ran something and we just got the mass numbers out, but we don't know what the percentages are. Well, let's see if we can figure out what those percentages are. So we can look at this by understanding that if I have two isotopes, my two isotopes need to add up to a whole. Okay, so my chlorine 35 and my chlorine 37 need to add up to 100%. Or 1, because what is 100% in decimal form? It is 1. Okay, and so I can say, all right, that my chlorine 35 is equal to X. Well, if chlorine 35 plus chlorine 37 is equal to 1, chlorine 37 then needs to equal 1 minus X. So if I have X and 1 minus X, can I solve? Yeah. So we can set up some algebra here. Okay. So my chlorine 35 has a mass of 34.96885. Okay, and it is there at X%. My chlorine 37 has a mass of 36.96590, and we assigned it a percentage of 1 minus X. And they all equal 35.453. Okay, so once again, algebra, system of two equations. We can solve for X and then plug X in and figure out both of them. All right, so we're going to combine like terms. We're going to distribute. We're going to do all the things. All right, so 34.96885x plus 36.96590 minus 36.96590x is equal to our 35.453. All right, so we did our distributing. Now we'll combine our like terms. We'll get negative 1.99705x is equal to negative 1.51 2, 9. Okay, this is okay at this stage. These are both negative. And when I solve for x, I'm doing a division. Well, a negative divided by a negative gives me a positive, which is good because if I'm looking for a percent distribution on something, well, I can't have a negative percent, right? I can't have a negative amount of something that exists. So I should have a positive percent. And indeed, when we solve for x is going to equal 0.7577. Okay, so my chlorine 35, if I turn my decimal x into a percent, I'm going to get 75.77%. My chlorine 37, I'm going to take 100% minus 75.77%, and I'm going to get 24.24%. Okay, now that may be a little off on the rounding there because when I punch these into my calculator, I carry everything. When I write the final answer down, then I'll round it off like I did here, but on my calculator, I carry everything. So you might be off depending on if you rounded and then subtracted or you carried everything on your calculator. You might have gotten 24.23%. It just depends on if you carry everything on your calculator. Okay, so that is a review on our atomic masses and our percent distribution with our isotopes.